Good morning. Welcome back to the second day of PyCon Sweden 2021. And we begin the day with our first keynote of day two. So today we are very happy that we have Alexey, who will present the keynote for us. So Alexey is a senior software developer at Elsa Automate in Finland, where he builds automation solutions for mobile networks. He also holds a PhD degree in space physics and is a founder of Race of Space company, which provides space research software for the European Space Agency and several universities. In his spare time, he develops Referred, a web editor for scientific writing. And today, he will share us about his work on managing cloud infrastructure as code in Python. So, Alexey, the floor is yours. Please go ahead.
Thank you, Steven. Thank you for having me today here, and thanks for the great introduction. It's a bit unusual not to see the audience, but you can still have breakfast, so enjoy. Today I will talk a bit managing infrastructure as code in Python. We will cover why is it a thing, why it's important, and what's available in Python. So Steven already introduced me really greatly. I live in Finland, in Helsinki, work in Elisa Automate, have a PhD in space physics, and over years I did a bunch of side projects. One of those is Refereed, online editor for scientific writing, with which I went through a Keynote accelerator also. And basically, I've learned most of the infrastructure as code concepts actually while coding Refereed during long evenings. So this is our plan for today. First, we will briefly overview what is infrastructure as code, why is it important, what's available, what tools are available. Then we will see what tools are available in Python for managing your infrastructure. Then we will go through a brief demo. We will see how we can develop and deploy infrastructure together with business logic on one of the public clouds, so that way it will be easier to see all the benefits of this approach. And then we will discuss the cloud agnostic approaches to managing infrastructure, what's available there, and how we can overcome this hurdle. And then we will conclude. So why infrastructure as code? So I will start probably with a brief story. Back in the day, when I was still doing my studies at university, I also worked as a part-time web developer. And for one of the projects, we were asked to develop a website for a football team. And football team belonged to a big company. So what the big company did, they bought us a server, put it in a server room in the rack, and just told us, like, do whatever is needed to be done. So I was the one who had to set up all this stuff. Yeah, let me tell you that were 2 very long and very cold days. So before automation, basically, you had to do all the infrastructure setup manually. First of all, it was, of course, painfully slow. Like you had to go from server to server, manually set up stuff. Also, it was prone to human errors because you mostly had to rely on your own experience and your own knowledge. So you could easily introduce some errors into the process. And then such infrastructure is very hard to maintain and also nearly impossible to replicate. Such ways of managing infrastructure are usually known as snowflakes. So it means that when you commission the infrastructure, everything works fine. But basically, it's very hard to replicate. And if something goes wrong, it's very hard, to recover from a critical failure, for instance. So on the left is a real picture of me setting up servers for a football team. So after, later on, after several tech unicorn startups appeared and the cloud was introduced, it was quickly obvious that it wouldn't be possible to scale while managing infrastructure manually, just because it's just way too slow, way too expensive. And system administrators started to incorporate their experience and knowledge into scripts, into some software that could manage infrastructure. So that way the IAC actually was born. So infrastructure as code, generally speaking, is a concept of provisioning, configuring, and managing and maintaining infrastructure. So with such an automated approach, obviously, it was the process became much faster, it became more cost-effective, and it was easier to replicate infrastructure. And that was like really important because you could, for example, spin up development and production environments, and they would be actually the same. Or you could easily recover from relatively easily recover from a failure, for example. So why many IAC tools? Oh, wait, so actually IAC brought even more benefits to the infrastructure management. First of all, since IAC is expressed as code, as machine-readable code, or configuration files, it's become possible to version control the infrastructure. So you could put up your infrastructure definitions into version control repository, and it became easier to see actually the history of how infrastructure changed. It also became possible to test infrastructure. Sometimes it actually depends how infrastructure is defined. If the language for infrastructure definition allows for testing, then you could actually test it also. And it also decreased the gap between DevOps teams and software developers. So for example, when you deploy some new changes to the infrastructure, other people in the team could easily code review those changes. And yeah, so more people in the team actually know what's going on with the infrastructure, which is good. So why many infrastructure as code tools? Like, why not build one? Because like probably over the years, there should be some set of best practices of how you are supposed to manage infrastructure. Well, this is quite complicated. First of all, different IAC tools cover different phases of infrastructure lifecycle. Some tools cover only the provisioning of the infrastructure, which means setting up virtual servers, virtual machines, and setting up networking and so on. Some IAC tools focus on configuration phase, meaning installing databases or web servers on already provisioned infrastructure. And some tools focus on maintenance phase and facilitate the deployment of the application logic actually to the infrastructure. Also, when after several public clouds were introduced, they diverged pretty quickly in the details of their cloud offerings, and it quickly became impossible to describe the infrastructure for different clouds in the same way. There was like subtle nitty-gritty details about the clouds, and so most of the tools became cloud specific. The IAC tools also differ by their approach. There are declarative and imperative tools. With declarative tools, you basically describe the state into which you want the infrastructure to arrive. And the system just figures out how to go from the current state to the next. With imperative approach, you tell the system how to get to the next stage. So basically, you tell like in steps what to do. Well, arguably, imperative approach is a bit more flexible, but declarative approach is much more readable. So imagine with imperative approach, you have to like follow all the commands, keep them in your head, and then imagine how the system would look like in the end. With declarative approach, it's much more easier. You just look at the description of the whole infrastructure. It's just so much easier, and easier actually also to see what changed, like what are the historical changes to the infrastructure that were made. IAC tools also differ by the languages they use for the infrastructure definition. So some tools use Turing incomplete languages. By that I mean like static configuration files or custom languages that were developed specifically for the purpose. And there are Turing complete approaches which use like fully fledged languages, for example, Python. That gives lots of additional benefits, as you can imagine, because like first of all, you have access to all the language-specific data structures, for example, and also you have access to the whole plethora of community-developed libraries, and you have access to all the tooling, to tests, and so on. So here is the current landscape of ISC tools. I segmented them by being cloud specific on the right and cloud agnostic on the left, and by Turing incomplete in the bottom and Turing complete on top. So in the bottom right, we have the configuration tools for all three major public cloud providers. So these are AWS CloudFormation, Azure Resource Manager, and Google Cloud Deployment Manager. All of those use static configuration files to describe the infrastructure in a declarative way. In the bottom left, we have a bunch of cloud agnostic tools, which also use either configuration files or custom languages. So the most notable examples from here are probably Ansible, which uses an imperative approach to infrastructure definitions, and HashiCorp Terraform, which uses the custom developed Terraform language to describe the infrastructure in a declarative way. And the top part is the one that will interest us today. In the top right, we have the AWS Cloud Development Kit, which is available in several languages, including Python. And what it does basically is that you can describe the infrastructure using Python, for example, and it will synthesize a CloudFormation template for your infrastructure and then send it to Amazon. So it's a declarative approach, and the state for the infrastructure is managed by AWS itself in the AWS CloudFormation backend. On the left, we have Pollumi and Cloud Development Kit for Terraform. So Cloud Development Kit for Terraform is quite similar in approach to AWS CDK. Basically, you can describe the infrastructure in several languages, and it will formulate it in Terraform language. And there is Pollumi also. Pollumi is a cloud agnostic tool, which is available in Python as well. So it is cloud agnostic, and it is interesting that, for instance, it relies on state management. Like it manages the state by itself. So basically, it formulates the definition files for the clouds, for the infrastructure, but it keeps the state to itself. Okay, so next I would like to show a small example of what's possible, like what's possible with infrastructure as code. So we will start with the AWS CDK example, and we'll build a simple REST API using a couple of managed services from AWS. So we will use API gateway service on the left and Lambda function service on the right. So API gateway is a managed REST API from AWS, and Lambda, you can think of it as a like small compute virtual machine, which is meant to be used for single purpose and not very long computations, like for example, for answering one of the endpoints of the API. Okay, let's dive into the code. So in AWS CDK, in its Python version, all the infrastructure parts are expressed as constructs. There are low-level constructs and high-level constructs. And high-level constructs can consist of multiple low-level constructs. So basically, this is how you construct more complicated infrastructure units from from low-level units. And all the constructs are packed into stacks. So stack is basically a combination of several AWS resources. So here we define my app stack, and we define inside of it the HTTP API construct, which is basically an instance of a REST API. Okay. And next, we want to add a route to this API to add an endpoint. So first, we create a Python Lambda function using the Python function construct. Then we define a Lambda proxy integration, which basically you can think of it as a bridge between the API and the Lambda function. And then we add a route to the path hello, which would answer the method get, HTTP method get, and which will use the Lambda integration, which we defined previously. And our Python function is our Python function for the Lambda is trivial, just hello world for now. Then we can actually just deploy this infrastructure using CDK deploy, and we will have our REST API in the cloud. Okay, so one interesting thing about it is that you don't even need, for example, if your Lambda function depends on some other Python packages, you don't even need to provide those together with your code to AWS. You only have to provide requirements.txt file, and the cloud will manage everything by itself after that. So let's make things a bit more interesting, and let's create a CICD pipeline for our application. And for this, we will use another managed service called Pipeline. This service will process the infrastructure definitions which we provide to it, make the changes to the infrastructure, and deploy the resources which we defined. Here's how it's done. So we define the pipeline stack, and inside the pipeline stack, we define the code pipeline instance of the code pipeline construct. And inside the construct, we tell the construct how actually our infrastructure should be synthesized. So we tell that it should install AWS CDK, it should install all the requirements, and it should synthesize the CloudFormation templates for us. We also say that Docker should be enabled for the synthesizing step. This is required, for instance, if our Python function includes some requirements. So in that case, AWS spins up a Docker container and installs the requirements inside the Docker container. And then we add to the pipeline a stage. And the stage is basically our application stack, which we defined earlier. So after that, we can deploy our infrastructure. We have to do this only once, actually. And then we can commit this code to the Git repository. After that, this pipeline will actually pull the code from the Git repository, process it, and deploy the resources, and deploy our REST API. And after that, actually, we don't need to deploy our infrastructure by hand anymore. We only commit it to the repository, and then it processes itself. Okay. And on the right, you can see just a screenshot how it would look like in AWS console. We have like several steps of the pipeline. First, it pulls the code, then it synthesizes the template, then it makes changes to the pipeline if it's required, and then it will deploy our resources. So now we can start enjoying the benefits of the IAC approach. For instance, we can start adding tests to our infrastructure. So the most trivial way of testing infrastructure would be snapshot testing, at least in the case of AWS CDK. Because it synthesizes CloudFormation templates, we can check whether the template has changed after the previous time. And if it didn't change, it's fine. For example, if we refactored our infrastructure definition code, we want to be sure that it didn't introduce some unexpected changes to the infrastructure. So here I define a simple test case for comparing the previously saved snapshots of the infrastructure to the newly synthesized one. And then all we need to do is basically push the code to the Git repository, and then something interesting actually happens. Our pipeline takes the code from the Git repository, processes it. If the tests are fine, if the tests are fine, it continues to process the infrastructure definition, and if there are changes to the infrastructure, it can change in the infrastructure. And our pipeline is actually a part of the infrastructure. So if there are changes to the pipeline, it can change itself. So there's a bit of recursion going on. So our pipeline processes the infrastructure definition, including for itself. So here I added also a couple of steps to the pipeline. I added the pre-step for the pre-deployment of the for our application stack, which runs the test, and the post-step for the manual approval of the new infrastructure. So basically, after the pipeline finished processing everything, we can go and review the changes to the infrastructure and approve or reject those. This can be useful, for instance, in production environments. And as you will quickly notice, the code that you write in AWS CDK to define the infrastructure is very much reminds you of a Python package. And actually, you can package your infrastructure as a Python package and distribute it. You can push it to the Python package registry, and other people could download it and use it. And there are a bunch of interesting packages already available. And that's, in my opinion, a very interesting way of thinking about infrastructure. So basically, you can provide pieces of infrastructure together with the application logic for distribution, and other people could download it and use it. There's tons of benefits to this. Like you can, for instance, define an infrastructure for assembling an HPC supercomputer and distribute it, and other people could download it, deploy it for themselves, and they have a supercomputer. Or you can use it in your team, like so that anybody in the team could download a package, deploy it, and have their own test environment. Yeah. So this way, the infrastructure actually turns out to be like a collection of small pieces of logic which other people could actually write, and you can assemble as something very interesting from these pieces. So up until now, we focused on a cloud-specific approach to infrastructure definition. So we were dealing only with AWS. And if we continue to do so, we will become so-called cloud vendor locked in. So with the more we rely on the managed services of a given cloud, the harder it is to go away from those services, because managed services are so different in different cloud offerings. But in my opinion, cloud locking is not necessarily a bad thing. There are tons of pros of using like a single cloud, being cloud native. First of all, it's the speed of development. Most of the managed services offered by the clouds are really good, and it would be quite difficult to create something on your own which will have the same level of resiliency and will be maintained as well. Secondly, if you use the managed services from the given provider, they will give you a better cohesion between different services of your application. Like, let's say maybe the easiest example is the authentication. if you use the authentication service from a given cloud provider, it will be so easy to plug it into other managed services of this provider. And also, you don't get to decide too many things. So there will be no analysis paralysis. You use what you get, and it's like, maybe it's not flexible, but it works. And instead of like doing research, you build an application. And of course, there are cons to the cloud lock-in approach. So obviously, it's difficult to migrate to a different cloud, and you find yourself in a position where you don't have lots of leverage on the decisions of the cloud providers. So, for instance, the pricing could change, or some managed service that you rely on could like be deprecated, and also limited decision making again. You don't get to decide what you use a lot, and it's like lack of flexibility for some. But if I talk, for instance, like about startups, cloud lock-in is a great thing actually. If you reach the point when cloud lock-in becomes a problem, then I'd say congratulations, like you made it. most of the startups like decline right before that. But let's say your application actually requires you to be cloud agnostic. There could be multiple like serious reasons. Like, for example, you require to install your software onto customer premises, for example. Or there are some political or governmental limitations that tell you that like where you can store your infrastructure, where you cannot. You can store your data. Then we can try the cloud agnostic approach. Well, the bad news is that the cloud agnostic tools are not truly cloud agnostic, unfortunately. So as I said earlier, the cloud offerings diverge so much at this point that it's really difficult to describe the same infrastructure with the same code for different clouds. So, and by cloud agnostic, most tools actually mean that they support the same development workflow for different clouds. The code will be different, but at least it will be familiar to you in a way how it's written. So what are the possible solutions to this situation? Many people try to solve this problem. The first thing that comes to your mind is like, let's build another layer of abstraction above cloud-specific IAC tools and like make it universal for different clouds. But again, some people tried, and you very quickly run into a wall of like nitty-gritty differences between the clouds. Another way of doing things is to standardize how the cloud architecture is described and like basically architected for different clouds. That would be great, right? But unfortunately, well, I don't see the motivation for the cloud providers to do so right now. Well, and the third solution would be to find some common denominators between the clouds, find some services that actually look and work similar and use those. And this way we can get to like almost cloud agnostic architecture. Here is one example of how it can be done. So we will rely on containerization, of course. We will write our infrastructure using Pollumi, which is cloud agnostic. And Pollumi is great in a way that it can manage not only the clouds, but also Kubernetes clusters. So we can use Pollumi to provision a Kubernetes cluster from any public cloud provider. All of them have managed Kubernetes services, which are pretty similar. Unfortunately, the code for provisioning those Kubernetes clusters will be different. Yes, but there's not a lot of code, fortunately. And also, we can use Pollumi to provision the managed container registry from any of the clouds. Again, the code will be different, but not a lot of code. And afterwards, we can use Pollumi for managing our Kubernetes cluster. So again, with this scheme, we arrive to infrastructure definition fully described in Python. Yeah, and it is cloud agnostic. You can actually even use like Kubernetes, manage Kubernetes services and manage container register from different clouds. This scheme will allow you to do this. But obviously, this is difficult. This will be a bit more complicated because you'll have to make more decisions, what to deploy to your Kubernetes cluster, how to make it scalable, how to make it resilient, and so on. More decisions will have to be made, and some of those will be wrong. Yes. So what I want to take away from the from today's talk is, first of all, it is fully possible to define infrastructure fully in Python already today, and it has lots of great benefits. In my opinion, the most important benefit is that all members of the team can contribute to the infrastructure code and review it, and it's like written on the same language. All the team can speak and write the same language and understand it. It is so much better when everybody understands what's going on. Secondly, this infrastructure will be version controlled, so you will always know who did what or who has more experience in which part of the infrastructure. It is testable because you are using Python, so you have access to the all the Python tooling. It is easily replicatable. You can even distribute your infrastructure. You can distribute parts of your infrastructure and so on. And it is fun to tinker with. Just try it out. That's what I wanted to tell you today. Thank you.
Thank you very much, Alexey. So perhaps we can go to the question and answer session. So please feel free to use the comment section in YouTube to write your questions, and it may pop up a little bit later because there is around a 30 seconds delay. But in the meanwhile, we already have a question from Alexander. So let me bring this up. So Alexander is asking, I work with customers who require to set up architecture completely agnostic, as some of the customers require on-premise hosting for legal reasons. Will Pollumi still be useful in these cases?
Yes, actually, this is one of the like legit reasons for going cloud agnostic. And if you deploy your infrastructure, for instance, as a Kubernetes service and at customer premises, then yes, totally, you can use Pollumi for that.
Yep. Okay, I hope this answered the question. So we are still waiting for more questions. But in the meanwhile, I do have a question. So in the beginning, so when you are showing the AWS pipeline, it actually looks very similar to how we write Docker recipes. So how would the containers, for example, Docker, fit into this landscape? We don't talk about Kubernetes like in the later case.
Okay, I'll just slide to that slide. Right. So Docker fits quite well into the scheme. So I can, for instance, give you one example, quite an interesting one that I had during referee development. So at one point, we needed to develop an API endpoint that could convert LaTeX into PDF. And so for that, you need to compile tech. And obviously, like, you don't want to compile it on your machine and then push it to the cloud. It makes things more complicated. Like, it's more difficult to transfer this stuff to other people, and you have to write additional logic of how to include the compiled binaries into the code that you push to AWS. But it is possible, for instance, to develop the Lambda layer, which will be kind of a plug-in to a Lambda function. And this Lambda layer could spin up a Docker container and do the compilation inside the cloud. So yeah, even such quite complicated schemes are possible. So you can push only the Docker file definition to the AWS, and it will compile everything there.
Yeah. Okay, thank you. So we have more questions. So we have a question from Kenny. So how is it possible to integrate AWS CDK with GitLab?
Okay. It will require a little bit more work, but not much, actually. I'll show you quickly. Okay, so here you can see, oh, no, not here, where was it? Yeah, here you can see one line, one parameter which we pass to the shell step construct is the input. It is called pipeline source connection. So this is the way how you define the connection to different repositories from AWS. I haven't tried how to set up the connection to GitLab myself, but I've set up connections to Bitbucket, which wasn't officially supported by AWS. So there are official connectors to GitHub, for example, so that it's very easy to set up the connection. But if there is no official connector to the repository, you can still set it up, but just in a little bit more complicated manner. You have to go through the authentication, and then AWS will formulate like the resource IRN to this connection, and then you can use it in your pipelines. So it should be possible.
Yeah, thank you. So for a following up question from myself. So how easy or how difficult would this be to integrate with external CI services like GitLab CI or GitHub CI with this setup?
Easily possible. I don't see any really. I think you lose some benefits. Let me think. Well, you lose some benefits, but it is possible. For example, if there are some changes to the way the pipeline works, you no longer can define it in your code. You have to go to the CICD provider and do it there. But it is doable.
Yeah. So we also have a question from Slavic. So corporations or firms from which countries dominate the IAC markets nowadays, both in terms of server location and developer from team location?
It depends what we mean by the IAC market, really. A lot of IAC tools are open source, and so they're not pushed by any corporation. Major clouds, they provide their own ways of managing infrastructure, and obviously, like those things belong to them. So it's hard to answer this question like definitely.
Yep. Okay, so we have more questions. So we have Ahmad, who is asking, does Pollumi have good tooling or extensions like Terraform?
Most likely, the market for extensions.
He added an extra follow-up, so it's tooling, extension, and providers like Terraform.
Yes, and actually, anybody could develop their like additional provider and additional extension to Pollumi, but as far as I can tell, the community is a bit smaller than Terraform. The project is a bit younger, but it's getting there, and I think the fact that it supports fully fledged languages will help, because not everybody likes to code in Terraform, really.
I see. Okay. A comment from probably Helio. So it's asking, I actually thought IAC includes the hardware infrastructure.
So the servers are already there, but by provisioning, I mean that you provision the virtual machines and like lower level infrastructure, like of course, in AWS, for instance, when you assemble something complicated like an HPC cluster, in certain cases, it will try to at least to locate the servers so that they're close to each other. So in this way, you can a bit control how the hardware is placed, at least, but you don't get to put a server into AWS. Yes.
Yeah, there is also the option of bare metal. Okay, so let's see if we have more questions. So I wonder, is this what you do, like fully embrace in your own company and so on?
And not fully. Well, in our case, we are in situation when we have to be cloud agnostic because Elise Automate solutions have to be installed on customer premises. So we have to use cloud agnostic tools. And for now, mostly we use Ansible for configuring the infrastructure.
Yeah, that's good. We've got a comment from Helio. Great talk.
Thank you.
Yeah. So if there are no more questions, I guess we can. Slavik was my comment. It's the wrong window. Thank you for answering.
It's great to see that IAC is a hot topic on this
Yeah.
conference. There were great talks yesterday by Magnus and Gunnar, which I followed. So
Yeah.
yeah.
Okay, so if there are no more questions, I guess we can end here. So again, thank you very much, Alexey, for giving us such an interesting talk on infrastructure as code. So for
Thank
the
you for having
audience, please feel free to follow the PyCon Sweden website, where we have the full schedule of all the talks today, and also please move the conversation to the Slack workspace. Thank you.
Thank you very much.